This is a Hurco VM1 CNC machining center. If you only know me as the guy who beats on rusty cars, that might sound like gibberish, but this is actually how I got started making videos. I was way in the weeds on industrial CNC machines. Basically, I bought a bunch of broken junk and tried to fix it myself. Some things never change. Anyway, back then, most machine tool content was made by and for hobbyists. You could find 700 videos about tramming a Bridgeport or dialing in a 4-jaw chuck. There wasn't a single video about aligning a machine after a crash or reading an electrical schematic and finding a fault in an e-stop chain. But that's the cool thing about being a human. If you want something that doesn't exist, you can make it. Now, I didn't consider that the reason no one was sharing that obscure tribal knowledge is that very few people had it, and even less people were actually looking for it. I'm trying to get back into it, but we're going to tone things down a bit. We probably don't need to discuss interpolation, trajectory planning, Modbus, FPGAs in painful detail. I find it fascinating, but that's literally just me. So let's start with the basics. What even is this machine, and what the heck am I going to do with it?
This is a drill press. It uses a spinning tool to cut holes. If you want to get a lot of pedantic comments, you might call this tool a drill bit. It can only cut in one direction. This is a milling machine. It's about the same as a drill press, but it has 2 extra axes of motion. If we use a slightly different spinning tool called an end mill and carefully turn these handles, we can cut in 3 directions. The CNC machine is really just a milling machine inside a sheet metal box. Instead of turning handles to move the axes, a computer moves them for us using electric motors. The computer can even move all 3 axes at the same time. It can also change between 16 different cutting tools automatically. It's basically a robot that makes solid objects into slightly smaller solid objects. It can make about any shape you can think of using instructions stored in a program. The program tells it where to go and how fast to move. The machine then decides if, when, and how to get there. That being said, this machine is actually pretty dumb. Even though it knows exactly where it is at all times, if we tell it to cut a big hole into itself, it will happily do it. And with 15 horsepower, moving at almost 1,000 inches a minute, you don't want to be anywhere near it when that happens. I'm using these digital calipers as an analog for the CNC machine. They both make very accurate moves by counting teeny tiny little tick marks called encoders. Computers are really good at counting, so as long as they're powered on, they never miss a tick mark and they always know exactly where they are. But right now they're not powered on. When we switch them on, they don't know where they are. They need to be calibrated. On the calipers, we move the jaws closed and push origin. That resets the counter to 0 at a known location. The machine does about the same thing. We push the calibrate button and it moves until it hits a physical switch, backs up to the index pulse on the encoder, and resets the counter to 0 at a known location. As long as we don't lose power, we should never lose the position.
Power outages are not good for CNC machines. That can get really expensive.
If we want to actually make something, we have to tell the machine what to do and where to go using a program. Here's a drawing for a very important part. We just need to move to 4 points that are 20 millimeters apart. With the calipers, that's really easy. We just slide the calipers so the 0 point lines up with the 0 point of the drawing. Our program just copies the location of the points on the drawing. The CNC machine is not so easy. The 0 point of the machine is never going to line up with the 0 point of the part. We're going to have to do some math to make up the difference. Luckily, we don't have to do that. The computer can figure it out for us. We measure the distance once and tell the computer to automatically add it to each location. I do that on the calipers by pushing this 0 button. I can toggle between the absolute location and the offset location. The CNC basically works the same way. We move it to a 0 point and use this store location button to create an offset. Now we have a machine position and a part position, and the part position should match the drawing. The caliper only has one axis, so it only needs one offset. The machine has offsets for all three axes. It also has offsets for the tools. There's no way we can make all the tools the same length, so we use another offset. That does cause an issue though. There's a Z-axis offset for the part and a Z-axis offset for the tool length. When you have two offsets in the same direction, things get really confusing. Many controls, including this one, will let you set the tool length based on the active part offset. They will also let you set the part offset based on the active tool offset, causing this diabolical circular dependency. If that wasn't fun enough, this control has 5 part offsets, and for reasons that remain unclear to me, each tool has 2 separate, but not mutually exclusive, length offsets.
Don't feel bad if you didn't comprehend the whole offset thing. I've been playing this game for a long time, and I still struggle. It's very counterintuitive. You have to add to make things smaller and subtract to make things bigger. You start adding in rotary axes and things get exponentially more confusing. Problems with the tool and part offsets are the most common cause of scrapped parts and crashed machines. It is very confusing.
Lots of programs are still written by hand, and many controls, including this one, have simplified conversational programming where you basically just fill in blanks. If you're good with computers, they can do a lot of the work for you. CAD software lets you build a part virtually, and you can tweak the design as many times as you want. You can even build up whole assemblies and see how things fit together. This is a mechanical advent calendar I designed for my son, but ran out of time to build before Christmas.
Well, there's always next year.
CAD is extremely powerful, but it does make it very easy to design parts that are cool looking, but almost impossible to actually make. Although with 3D printing, that's not as true as it used to be. It's also easy to obsess over details that look huge on the screen, but in real life, they look like this. CAM software uses the CAD model to make the program. Again, we can machine it virtually and tweak things as many times as we want. Then we just send the program to the CNC in a standardized language called G-code. But like all good standards, everyone's standard is a little different. So we use a translator called a post-processor. Usually every machine requires a unique post-processor. I just tweaked this one a bit to force it not to turn the spindle on when tapping and delete a bunch of stuff we don't need, like the chip conveyor. Years of programming production parts has made me very fussy about my code. Too fussy. Getting the program into the machine is a little challenging. It does have a floppy drive, but I'm just going to shove the ones and zeros through the serial port using this RS-232 cable at a whopping 9600 baud. I realize it seems insane that a machine built in 2005 is still running DOS with a whole 46 megabytes of memory and 16 glorious colors. If you want to mess around with industrial gear, it's just something you have to wrap your head around. A lot of this stuff was standardized back when computers looked like this, and now we're basically stuck with it. These machines prioritize reliability and nearly indefinite backwards compatibility. That means the hardware is usually a decade or two behind the times, and the software is chock full of clunky legacy baggage. I know for a fact in 2019, Fanuc, the largest robotics company in the world, was still selling brand new controls with monochrome CRT monitors running 486 processors. I was there when they installed one. There is an upside to this perpetual CNC design permanence. If you know how to run a brand new Fanuc 31i control, you can walk up to a 6M control built in 1979 and run it with minimal or possibly no training. You could also download a program using an RS-232 cable, take that program back to your brand new machine, upload it using the same cable and the same software, and I bet that program would run with minimal or possibly no editing required. There are thousands of 6 Series CNC controls still making good parts. I know because I used to have one. Okay, we've got a 20-year-old machine running untested code on an unfamiliar control. What could possibly go wrong? I guess let's assume the CNC machinist's position and push the big green button. What I usually do is let the tool get close, then stop and just do a reality check.
It says we're at 1.7602 from the bottom of the part. Something's not right. It's too low. Why is it doing that? It's not the right spot.
Does it look like it's really where it says it is?
Okay.
If it does, in CAM we trust.
Well, that's not good. Stuck. No tool change. It's a little drippy.
This part is trickier than it looks. It has to be machined from 4 sides, which means we have to rotate it 4 times. Also, sharpish inside corners are really hard to make. I don't know how you would tackle that on a manual machine, but with the CNC we can cheat. I just left a little bit of meat in that area and then nibbled it out from the top side.
I'm really glossing over the whole programming part because it's kind of boring. There is so much to it. Tool selection, fixturing, feeds and speeds. This is a whole trade. CNC programming, manufacturing engineering, and I'm barely scratching the surface of what's possible with more complex 4 and 5 axis machines. You can spend your entire career figuring this stuff out.
There's also a tiny 440 threaded hole. This machine has rigid tapping, which seems like it shouldn't even be possible. Somehow the machine perfectly synchronizes its motion to thread the tap in, stop exactly at the bottom, and then thread the tap back out.
I think that worked. That's it. No, I'm wrong. There's one more operation. Stand by.
I can't get much taller than that without a stool.
I made a thing.
Oh, okay. What is it?
It's a part.
It needs to be filed inside.
It does need to be filed inside. I did not deburr properly.
It's light. I thought it would be heavier. It looks heavier.
It's because it's made from aluminium.
Oh, is that the same thing as aluminum?
It is in this country.
Okay.
Okay, that's our first part. I think it looks pretty good. It's actually for my mom. It's a replacement part for this gizmo, which is it's like a level winder that you see on fancy fishing reels, but this is for a spinning wheel that turns wool into yarn. The original part is 3D printed. There was a bit of a design flaw. They might have gotten away with it if they'd made the screw just a little bit longer.
I think the batteries are dead. In case it wasn't obvious, I come from a long line of people whose hobbies are really just work.
Having machined one tiny part from butter soft aluminum, the next logical step is to hog into a gnarly chunk of high carbon 4140 steel. This is what we're building. It's an axe. Sort of. It'll make sense when it's done. Maybe. There's really nothing straight or flat to hold on to, so we're going to need a fixture. These are soft jaws made from aluminum, and we can machine them to fit the curvy shape of the axe head. This is a very powerful technique for holding on to oddly shaped things.
That's not right.
Well, it's actually working better than I expected. There's a little bit of chatter, but I think it'll be fine. There's a hole for the handle. It's called an eye. Axe terminology is oddly anthropomorphized. You ever wondered why it's shaped like that? Yeah, neither did I until I had to make one. Here's my theory. Until about 100 years ago, axes were made by folding whatever mild steel you could find over a small piece of high carbon steel and forge welding it all together. You naturally ended up with this teardrop shaped hole for the handle. Axe handles were standardized around that shape, and now we're basically stuck with it. Modern axes are forged from a single chunk of steel, and the eye is formed with a punch. Punches don't like sharpish inside corners. You can see they've cheated a bit on these modern axes and rounded it over, but the shape is mostly the same. Yeah, that was a very long-winded way of saying axe eyes are a pain to machine. And it sounds like we've just had our first casualty.
That's the end of that one. The sliver factory is open for business. There it is. That might be one of the coolest things I've ever made, at least on a CNC machine. I'd say somewhere between 55 and 60, Rockwell C. Time to temper. There is an upside to this perpetual axe design permanence. You can walk into a hardware store today and buy a replacement handle for just about any axe that's ever been made. Except for this axe. That's okay. I've got lots of CNC machines.
Machining high-strength wood is a whole lot less stressful than high-strength steel. It's amazing how far you can push it. I've been using this little router for 6 months or so, and I've broken 2 tools. Both times, it was because the tool fell on the floor when I loosened the collet. If you want to question your life choices, try designing an axe handle in CAD. I spent way too long on this, and I still didn't get it right the first time. They're only different by about 2 millimeters, but this one feels great. This one feels like hot garbage. I probably should have used something better than a half-rotten deck board from an old trailer, but here we are. Not too shabby. Might have gotten a little carried away with the taper on the eye. 3 degrees might have been a little too much. It shouldn't come flying off. That's always good. Are you a welder? Are things around you always catching on fire? Introducing Chippy, the world's first combination welding and firefighting tool. Made from hardened 4140 steel, Chippy stays sharp, unlike other chipping hammers. With a classic profile and compact size, Chippy is perfect for fighting fires. It's also handy for data security, fine woodworking, and 1/3 scale forced entry. It also looks really cool.
Did I need a chipping hammer that looks like a miniature fire axe? Probably not. But that's the cool part about being a human. If you want something that doesn't exist, you can make it. Especially if you have a CNC machine. There is a slight problem. I mean, besides the fact that this consumed more of my life than 6 seasons of Community, and the steel alone cost twice as much as a high-quality factory-made chipping hammer, I thought I was making a slightly funny, but still very practical tool. I accidentally made an heirloom quality tool that is way too nice to actually use. I wish I could say it was the first time. All right, thanks for watching. I hope you enjoyed whatever this was. By far, this is the most time I've ever put into a video. You might even say it took me 8 years to make. Also, thanks to the folks on Patreon who throw in a few bucks. It is very fun to be able to make videos that I find interesting, even if I'm the only one.